By now, you've been working with the gas laws. Boyle's law, Charles's law, Avogadro's law a little bit, uh, Gay-Lussac's law, the combined gas law. Well, and also if you're taking honors chem, maybe even the ideal gas law, PV is equal to nRT. Well, as it says here, gas laws predict how a gas is going to behave under certain conditions, starting conditions and then ending conditions, but it doesn't tell us why they behave that way. For that, we use kinetic molecular theory, also shortened KMT of gases, and that's going to help us explain gas behavior, and it predicts the outcome of experiments that are done on gases. Now, this is a simplified model, and what happens is we're going to have a list of how gas particles, atoms or molecules, behave, and any gas particles that follow these rules are called ideal gases. No actual gas is an ideal gas. Some gases are closer than others. The smaller the gas, the closer to ideal gas behavior, but all quote unquote real gases do not exactly conform to the assumptions you're going to see down here below. A couple of things to remember: all gases behave closest to ideal gas behavior with low pressure, high temperature. Low pressure, high temperature. You have to know that. It shows up a lot on tests for gas laws. Again, the smaller the gas, the real gas that is, the closer it is to behaving like an ideal gas. The closest is going to be hydrogen, which is H2. Helium is next. You would take a look at their atomic masses and compare the different choices if it was a multiple choice question. And then please always remember, temperature defined in chemistry is the average kinetic energy of the particles that make up a substance. Let's take a look at how gas particles are treated as ideal. Before we continue, I just wanted to say thank you to my students, a big shout out to them working from home here during this whole coronavirus, and anybody else that's working on chemistry. You should be proud of yourselves for hanging in there, doing the work. Do a little bit of vitamin chemistry or vitamin C every day, and let's finish this up. When it comes to ideal gas particles, then, these are the rules or assumptions that we're following with this model, that ideal gas particles are only moving in straight lines, no curved paths, completely random. There are no forces of attraction between one gas particle and another, that the volume that gas particles would take up, we're ignoring. Negligible, which I can't really say very well, just means we're ignoring gas particle volume relative to the total volume of the gas in whatever container it's in. And then, of course, these particles are constantly moving randomly. They're going to collide with each other and the sides of the container, but they're all elastic collisions, no net loss of energy. On the other hand, when you have real gases, the atoms or molecules that make up a gas, they're not going to just travel in straight lines. They could be curved paths. Of course, there are going to be forces of attraction. Even nonpolar attractions, there's still a force of attraction. Gas particles do have a volume. Yes, it's small relative to a container, but there is volume. And of course, collisions could be elastic or inelastic, and we might end up reducing the total energy of a gas. Why do I say this? You have to know what the ideal gas particles are following here, along with what I already typed up that we went through, right? That real gases behave closest to ideal gas behavior under conditions of low pressure and high temp, that the smaller the real gas, the closer it is to behaving like an ideal gas, and temperature is the average kinetic energy of the particles that make up a substance. These facts, along with these assumptions with gas particles, show up on every Regents exam in chemistry and pretty much every chemistry exam. I'm going to give you some examples now of kinetic molecular theory and these facts regarding ideal gas particles that have shown up on the Regents Chemistry exams, the three latest exams. This is question 12 from the January 2020 exam. Which statement best describes the particles of an ideal gas based on kinetic molecular theory? Not so great with drawing lines, but I can tell you, you need to know how we describe an ideal gas, right? Ideal gases, we're saying there are no attractive forces, cross it out. We're saying they're only moving in straight lines, so cross out number 2. We're saying that the collisions are not reducing the total energy. So the only answer it could be, and it is choice 4, that the volume that the gas particles take up is very small, or we're going to ignore it compared to the total volume of a gas. Let's move on to another Regents exam. All right, this is question 18 from the August 2019 Regents exam. According to kinetic molecular theory, which statement describes particles in a sample of an ideal gas? It almost sounds word for the one from January 2020. Particles are constantly moving in circular paths. No. Particles collide, decreasing total energy. No. Particles have attraction forces. No. Particles considered to have negligible volume. There it is, our answer again. We got one more we're going to check out, and that is June 2019. Okay, here we are. Question 16. Which statement describes particles of an ideal gas based on kinetic molecular theory? Well, here we go again. The volume is considered negligible. Well, that looks like our answer. We're ignoring gas particle volume. But let's take a look. Force of attraction between particles is strong. We're saying if it's an ideal gas, there is no force of attraction. Number 3, particles are closely packed in a regular repeating pattern. Well, wait a minute. That would be for a solid, not a gas. Not number 3. And then finally, particles are separated by small distances. Not with a gas, they're going to be far. So in this case, the answer was choice 1. I hope you see 3 out of 3 Regents exams right in a row have a question about kinetic molecular theory. And they could flip it and ask you what's describing a real gas instead of an ideal gas. These concepts show up all the time. Go over it, make sure you know it, and keep working hard. And thanks for watching.